All right, so let's try to summarize what we've learned in this section, and we'll start with continuations. That was the first thing we looked at, basically the idea that if you've got a task, you can call continue with on this task and specify yet another task that would follow this one, and you have your customization options. For example, you can provide a cancellation token. You can once again feed in the state using this object notation that we've seen before. Then we looked at the fact that continuations can be conditional. So for example, you can specify that the continuation will not fire if the task has faulted, meaning it's thrown an exception. So these are some of the ways that you can sort of determine which path the invocations take depending on whether the invocation of the original task was successful or cancelled or it caused an exception of some kind. Then we looked at different ways of arranging continuations. We had this idea of one-to-many continuations. Basically, you only continue when all of the dependent tasks are complete. And we also had a one-to-any continuation. That is the idea that we basically wait on any of the tasks to be complete in order to continue from this task. One thing I want to add here is you have to beware of situations where you are waiting on continuations that might not occur. Keep in mind that a continuation which is specified as not unfaulted will not occur if your original task has faulted, which means if you're waiting on this continuation, you're going to be waiting forever. You're effectively stuck. So this is something you have to be very careful with. After continuations, we looked at child tasks, the idea that we can have just detached tasks, which don't really mean much because it's just a task created within another task, and there is absolutely no difference to just making an ordinary task. It's just being created inside of a task, but so what? Who cares? It follows roughly the same rules. However, we also looked at the attached tasks, and these are more interesting because if you provide task creation options attached to parent, this affects on what happens if you wait on the parent. So if you wait on the parent, for example, you're also going to be waiting on the child and waiting until the child completes before the parent's wait actually releases. Now, it has to be said that child tasks can be continuations, and we've seen examples of those as well. Now, finally, we looked at different synchronization primitives. We looked at lots of them, but really, I'm sure you've been paying attention and you've noticed that they all roughly do the same thing. So they essentially have a counter of some kind and they let you execute end threads at the same time. So they check this counter, and the other threads, they are waiting, but they are unblocked as this counter kind of changes. So we looked at barrier, which is the thing that you want to use if you're making some sort of multi-stage algorithm and you want all the threads to finish one chunk of the algorithm and then synchronize and then finish another. So essentially the idea with the barrier was that you block all the threads until exactly so many threads are waiting, and then you let them loose, you let them through, and you once again block for the next chunk of threads. So you effectively wait until they are all at the same stage. So this is done by signal and wait. In essence, what happens with signal and wait is you're fusing both the idea of waiting until the value of n is a particular number as well as signaling so as to change that number. So you reach a point, you're basically saying, hey, I'm there too, and once everybody's there, everybody can go through. So that was one thing. Then we looked at countdown event, which kind of breaks apart this idea of signaling and waiting. So they are now separate, and you can call signal to actually signal on a countdown event, and once this reaches 0, then anybody who has been waiting gets through and gets to execute whatever they have to execute. Then we looked at manual reset event and auto reset event. Once again, the Slim edition is a kind of streamlining that's been introduced in .NET Framework 4. That basically means that the original class didn't have the Slim name and wasn't as efficient. So the manual reset event and auto reset event, you can think of them like countdown events, but with a count of 1. So there is just a signal which is either set or it's not set. And on some threads, you're waiting for the signal to be set. And on another threads, you are in fact setting the signal. Now, the difference between manual reset event and auto reset event is that as you're waiting on the signal, once it's been set, once you're allowed to execute with the auto reset event, it then resets itself once again. So if you do a second wait, then once again you're waiting for the signal to appear, whereas for the manual reset event, once you set it, you kind of set it forever unless you explicitly reset the condition. And finally, we looked at semaphore slim. Once again, there is the slim addition there. So the idea is, once again, you have a counter, and every time you wait on something, you decrease by a certain amount, and every time you release on something, you increase by a certain amount. And we saw that the semaphore can also have a maximum in terms of this count value that you can have. So these are some of the synchronization primitives which I hope help you synchronize your concurrent task execution.